In this section, we'll be discussing exponential growth and decay models. Many natural phenomena have been found to follow the law that the amount of A varies with time t according to the following function. This is a function for the law of uninhibited growth. In this function, we're trying to determine the amount that will be left after a certain time period t has expired. A sub 0 is the original amount when t is 0. E is a number, 2.71828 run-on decimal that's in your calculator. This is not a variable. K, which we'll be discussing in a moment, is the growth rate. And T is the time period. How long do you want to watch this particular model grow for? So to give you an example of the uninhibited growth, let's look at an example in graphical form. If we start with the amount at A sub 0, being time is down here and the amount is on the vertical axis, we start with A sub 0. That's the initial amount. Uninhibited growth follows an exponential growth pattern. We know it's growth when K, which is our growth rate, is a positive number. However, if K happens to be a negative number, that means we'll have an exponential decay problem. That means we are losing amount day to day. So if it's a decay problem, we start with a lot initially of the substance, and then we lose an amount exponentially over time. So these are two examples of what exponential growth and decay would look like. The formula is always the same. The only difference is the K. If the K is positive, then it is growth. If the K is negative, then it is decay. Now if we look at a couple other definitions of uninhibited growth, we could look at this particular growth model, which is the same formula that we had up above. All they did was change out N for A. This is the number of cells in a culture. Instead of amount, we'll call it N for number of cells, but the formula is still the same. Since K is positive, that means this is a growth exponential function. Again, N sub 0 is the initial number of cells. Since K is positive, it represents the growth rate. So K is called the growth rate of the cells. Another definition is doubling time. Doubling time is the amount of time that is needed for an increasing function to double in size. So in other words, how long would it take for whatever you started with to be twice its size? For example, a colony of bacteria grows according to the law of inhibited growth according to the function N sub t equals 90 times e to the 0.05 t power. N is measured in grams, t is measured in days. So let's first determine the initial amount of the bacteria. Well, the initial amount is always going to be the number in front of the E. So the initial amount of bacteria that we have is going to be 90 grams. The growth rate of the bacteria, well, you can see that the growth rate is up here. This is K. So K is 0.05, and remember, it is positive because it is growing, which represents 5%. So it's growing at a rate of 5%. So what is the population after 5 days? Well, if T is 5, we're looking for the number of bacteria after 5 days. So we plug 5 in for t. So 90 times e to the 0.05 times 5 power. And when we plug that into my calculator, we get 90 times e to the power of 0.05 times 5, and we find that the population after 5 days is approximately 115.6 grams. How long, so what is t, will it take for the population to reach 140? So I have the future amount. What I don't have is t. So we're going to take the future amount and we're going to plug the 140 in for the left side, and then we have to solve this for t instead. So it's exactly opposite of the last question. In the last question, you're given t and you have to find the future amount. In this question, it said, here's the future amount, find how long it will take. So we're going to put in 140 for the future amount equals 90 e to the k, which is 0.05 times t power. And we have to solve for t. So first thing we do is we get rid of the coefficient in front of the x, because I can't take log of both sides until that 90 is gone. So that means I have, on the left-hand side, 140 divided by 9, well, that simplifies to 14 over 9, equals e to the 0.05 t power. Now, in order to bring that t down in front, I'm going to take natural log of both sides. When I take natural log of both sides, I'll have natural log of 14/9 equals, and then that comes down, 0.05 t natural log e. Well, we all know that natural log of e is equivalent to 1, so we can cancel that out. Then, in order to get TL by itself, we're going to divide by 0.05 to both sides. So lastly, I'll have t equals natural log of 14/9 over 0.05. An approximate answer for how long that is, I could put into my calculator. So we'll have natural log of 14/9 divided by 0.05, and you're going to have approximately 8.8 days. For part E, what is the doubling time? Again, it's asking for t, just like it was in the last question. So this time it's saying, what is t in order for it to double? Well, I started with 90, so doubling that would mean I want 180 grams in the future. So I'll do the problem, I'll set it up exactly the same way, except for I want 180 grams in the future, meaning twice as much. So we're going to set it up just exactly like I did the last problem. So I want 180 grams equal to 90 e to the 0.05 t power, and I need to solve for t. Well, if I do all of this math, I could do all of this all over again. But a shortcut would be, if I've already done all the math and solved for t, and I know t is equal to this, all I have to change is the number on top. Remember, here we simplified 140 over 90 into 14 over 9. So couldn't I just put 18 over 9 here and solve the same way? So I'm going to use that shortcut to my advantage. So t equals natural log of 18 over 9 over 0.05, and that will get us our answer a lot faster. Remember, 18 over 9 is 2. 2 means twice as much content. I want double the population, and 18 over 2 is twice as much. That's where the 2 comes from. So when I put that into my calculator, I have natural log of 2 divided by 0.05, and it will take 13.9 days to double. Let's try another. This time we have a colony of bacteria that increases according to the law of inhibited growth again. So if the number of bacteria doubles in 4 hours, find the function that gives the number of cells in the culture. So this time it does not give me a formula. So I'm going to have to start from scratch, and I'm going to have to create a formula so that I can use it for future questions. This is the general formula for all exponential growth or decay problems. Let's plug in what we do know. I know that the bacteria will double in 4 hours. So double. It doesn't say how much I started with. So let's just pick any number. Let's say I start with 1 unit of bacteria. So that means in the future I'll have 2 because it has to be twice as much. So it wouldn't matter if you started with 50 and you double it to make 100, or if you started with 10 and you double to make 20. The proportion is still 1 to 2. E to the K, I don't know K because that's the growth rate. It doesn't tell me what the percentage at which this is increasing, but I do know T. In order to double, it will take 4 hours. So in fact, I know everything except for K. So why don't we solve for K so we can find the growth rate? So that's what I'm going to do now, is solve for K. So in order to solve for K, I first need to divide out the 1. But hey, dividing out the 1 isn't going to change anything. So to get that K down in front, I have to take natural log of both sides. So I'll have natural log of 2 equals natural log of e to the 4k power. And now that 4k can come down in front. So I have natural log of 2 equals 4k times natural log of e. And we all know natural log of e is equivalent to 1. So in order to solve for k, the only thing I need to do is divide by 4. So I have k equals natural log of 2 divided by 4. So k is approximately equal to 0.173. In other words, 17.3%. So what it's asking me now to do is find the function. Find the function. So I need to rewrite this function with the k that I have just now found. So I know any future amount, not just doubling time, but I can predict any future amount, given how much we started with, because now we know the growth rate of this particular bacteria. So let's use that information to forecast some future problems. So how long will it take for the colony to triple? Well, remember, it doubled in 4 hours, so it's going to triple. Obviously, it's going to take longer than 4 hours. So in order to triple, let's now change our formula into tripling. So let's use this formula. The future amount will be 3 times as much as the initial amount, e to the 173 t power. So let's solve for t. Let's take natural log of both sides. So I have natural log of 3 equals, I'll bring that in front, 0.173 t, natural log of e. Divide both sides by 0.173. So I have t equals natural log of 3 over 0.173, which is approximately equal to 6.35 hours. Remember, the time frame has to match the original time frame. So this bacteria doubles in size in 4 hours, triples in size in 6 hours. So how long will it take for the population then to double a second time? In other words, be 4 times its original size. So it's going to take even longer than tripling. So we're going to do the exact same problem over again. The only difference is now we're going to put 4 in this location because we want 1 unit to turn into 4 units or 4 times as large. So 4 equals 1 e to the 0.173 t power. And if we use this little shortcut over here, that means t equals natural log of 4 times its size over 0.173, which is equal to 8 days. I might have been able to guess that because if it doubles in 4 hours, when will it double again? In another 4 hours, which means 8 days. So now let's talk about decay. Decay is the same equation. Again, the only difference is that the K is now negative. So this number right up here is now negative. So we can't talk about doubling time because we're losing bacteria or amount of substance. So we will never double in size, but we can talk about half-life. It's the time needed for the function to reduce to half of its original size. So let's talk about carbon-14. If we originally have 60 micrograms, and it will decay at a constant rate of 0.0121%, the rate of decay is negative 0.0121%. That is the rate. It's a percentage. What would I put in then for K? Remember, K must be in decimal form. This is not decimal form. This is percent form that happens to have a decimal point in it, but it's in percent form. In order to create decimal form, I have to move the decimal 2 to the left. So K is 0.000121. And make sure it's negative because we do know that this is a decreasing function. So to determine its half-life, we're going to use the original equation where the future amount is equal to the initial amount times e to the k, which we now know, t power. So this is the formula we will use to find its half-life. In other words, what is t in order for this initial amount to be half of its size? So what we want to do is we want to plug in some values for the initial amount and the future amount. So if I start with 1, I want that 1 to now decrease to half of its size. And what would t need to be in order to make that come true? Well, remember, what I want to do here is solve for t. So to solve for t, I'll take natural log of both sides so I can bring that t down in front. Now that I have the t down in front, I can divide out its coefficient. And I have t. So that means t is equal to natural log of 1/2 divided by negative 0.00121, which is equal to 5,228 days. 728. It doesn't state what the time frame is. So I don't know. I'll just put units of time. It doesn't state whether it is in days or years or months or hours. So I'll just put units of time. So let's try just a couple more problems on this last page. We have strontium-90, which is a radioactive material, and it decays according to the function A of t equals a sub 0 e to the negative 0.0244 t power. A scientist has a sample of 500 grams. So first, let's decide what is K. Well, K is always in the exponential field next to the t. So K is negative 0.0244. Since it is negative, that means that this radioactive material is decaying over time. So the rate of decay, this is a decimal. K is always a decimal. The rate of decay is a percent. So we will move that decimal 2 to the right. So the rate of decay is negative 2.44%. So let's use this equation to find out how much is left after 10 years. So we're going to take 10, plug it in for t, and solve for the future amount. So how much will we have after 10 years? Well, we know we started with 500 grams, e to the negative 0.0244 t power, t is 10. So we just have to plug this into our calculator. 500 times e to the negative 0.0244 times 10 power, and we'll find that we will be left with 392 grams. So when will 400 grams be left? So find t when we know that the future amount is 400. So this time we have the future amount. Let's find t. So if the future amount is 400 grams, and we know we started with 500 grams, let's find t. First thing we do is divide out the coefficient. 400 divided by 500 we can leave as 4/5, or you can change it to 0.8 if you prefer. So 4/5 equals e to the negative 0.0244 t power. In order to bring that t down in front, we're going to have to take natural log of both sides. So we'll have natural log of 4/5 equals negative 0.0244 t times natural log of e. Always remember, natural log of e is equivalent to 1. That's why we can cancel that out. So our last step is to divide out this coefficient. Don't forget to take the negative with it. So t is equal to natural log of 4/5 over negative 0.0244, which is approximately how long? So natural log of 4/5 divided by negative 0.0244 will take us 9.1 years. Remember, the unit of time must match the unit of time that was given to us in the original problem. So finally, what is its half-life? Half-life is determined by determining how long it will take for the original 500 grams to equal half of its size, which would be 250. So this becomes basically the same problem that we just did. We're only changing 400. We're going to make it 250 instead, but everything else is the same, which means I can probably use this shortcut right here, which says t equals natural log of 4/5, but instead of 4/5, because remember 4/5 came from originally 400 over 500, so now we're going to put 250 over 500, and 250 over 500 is a half. So it's natural log of 1/2 over 0.0244 negative. So it's the exact same question. All I did was change this ratio, which came from the left side of the equation. It would have been 250 divided by 500, which is 1/2. So I'm going to do the exact same equation. I'm just going to change that this fraction is 1 divided by 2, and I'm going to find that it's going to take me 28.4 years.